Hello viewers and welcome to my YouTube channel. I'm going to conduct a lecture series in sequences and limits. Sequences is a fundamental topic in calculus and real analysis. Let us start with the definition of sequences. A sequence of real numbers is a function defined on the set of naturals. The set of naturals will be denoted by script n, which is equal to 1, 2, 3 and so on, whose range is contained in notation wise, we could write this as, suppose say capital X is the sequence, then capital X is a function from n to r. There are many ways to depict sequences. We could simply denote a sequence by x, by xn using parenthesis, or xn such that n belongs to the set of naturals using parenthesis. Now the only reason we are using parenthesis is to ensure that sequences have an order. Let us take up a few examples of sequences. So if I define x from n to r by x of n is equal to say minus 1 raised to n, where n is a natural number, then we are going to end up getting a sequence which could be written as. Now, for the first term of the sequence, we will put up the first value of n, which is 1, and we will be getting minus 1 raised to n, which is minus 1 raised to 1, which is minus 1. The first term of the sequence is minus 1. For the second term of the sequence, we will put up n equal to 2, so we will have minus 1 squared, which will be equal to plus 1. So the second term of the sequence is 1. The third term of the sequence, again for odd powers of minus 1, it will be minus 1. The fourth term, since 4 is an even number, we will have 1, minus 1, 1 and so on and so forth. This is the sequence x. We could also write it in a conventional manner in a shorter notation as x is equal to minus 1 raised to. Now there are multiple ways in which sequences are expressed. Let me take another example. Suppose we have a real number k. I can define a sequence k as k, comma k, comma k and so on and so forth. Such a sequence is known as a constant sequence. For the same k, I could define another sequence, say k prime, and k prime is given as k, k square, k cube, k raised to 4 and so on and so forth. Now this actually reminds of geometric progression. We could also define sequences recursively. Recursively in the sense you will be given initial terms of the sequence and there will be a rule to find out the successive terms. So let us talk about the Fibonacci sequence, which is one of the famous mathematical sequence. So we will denote the Fibonacci sequence by f. Your f will have terms fn. Now as a mean of the initial terms, f1 we are going to take as 1, f2 we are going to take it as 1, and the successive term henceforth fn plus 2 we are going to take it as the addition of the previous two terms. So we say that fn plus 2 is equal to fn plus 1 plus fn, and this is for n greater than equal to 3. If we were to find out f3, so f3 is nothing but f1 plus 2. So if you compare it with the above expression, your n is equal to 1. So let us put that value on the right side. So we will have f1 plus 1 plus f1, which is f2 plus f1. Now we have stated here that f1 and f2 both are 1. So the sum can be written as 2. So thus we get f3 is equal to 2. Now making it simpler and shorter, f4 is given as the sum of f3 and f2. f3 we had just evaluated above, it is 2, and f2 given to us is 1. So this is 3. And likewise, if you evaluate f5, you will get 5. Thus the Fibonacci sequence can be written as f is equal to, the first term is 1, the second term is 1, the third term is 2, which is the sum of first and second term, the next term is 3, which is the sum of the previous two terms, then 5, then 8, 13, 21, 34, and so on so forth. The Fibonacci sequences play a very crucial role in mathematics. They give rise to a thing called as golden number as well as the golden ratio, which you can actually find out in nature. So these are the few examples of sequences. We have taken sequences being expressed as a function, and we have also talked about the recursive definition of a function. Now moving on to the next topic that we are going to discuss today, it is limit. While we talk about limit, we are interested in what is happening to the sequences. Since it is defined for indefinitely many natural numbers, we are interested in what happens as you go on and on and on. So for example, let us just have a sequence. Say this is the first term, x2, x3, x4, and so on and so forth. So by limit, we actually figure out if these terms of the sequences are moving closer to a point called as P. If it happens so, we say that P is the limit of the sequence. If it doesn't happen, we say that P is not the limit of the sequence, and we end up saying that the sequence is going to be a divergent sequence. So we'll start with a sequence. A sequence x equal to xn in R is said to converge to a real number x if for every epsilon positive we can find a natural number positive such that the distance between xn and x is going to be lesser than epsilon for every n greater than equal to n. Again, let us have the number line. So if this is the number line of this, if this is the number line, let me denote it by script r, and this is the limit which we are saying that the sequence x converges to x. So if you take any radius for this epsilon, so let me take the radius as epsilon. So we will end up getting a neighborhood which will be x plus epsilon and x minus epsilon. The definition tells you that there will be infinitely many terms of the sequence xn. So your sequence will be x1, x2, then there will be some term of the sequence which will be xn naught. After this we will have xn naught plus 1, xn naught plus 2, and so on. If the sequence converges to S, for any epsilon, you will be getting a term of the sequence which serves as the first term of a tail sequence, and this entire tail sequence lies in this neighborhood. This real number x, this is said to be the limit of the sequence. And notation wise we write xn converges to x, or xn converges to x, or limit xn is equal to. If such a real number does not exist, we say that the sequence is divergent. If x does not exist, we will say that sequence xn is divergent. The definition which we have just seen over here, this is also classically known as the epsilon and not definition of convergence. So here we have the first example. We are talking about the sequence 1 by n, which is the sequence of reciprocals of the natural number. And we are saying that the limit of this sequence is 0. We could also write this as limit n tending to infinity of 1 by n is equal to 0. So we are going to take help of the definition we have just stated, the epsilon and not definition. So let me just read it one more time. A sequence x equal to xn in R is said to converge to a real number x if for any positive epsilon there exists a natural number n naught such that the distance between xn and x is lesser than epsilon for every n greater than equal to n. So if you will check the definition, so the task over here is that you pick up any epsilon. For this epsilon, you should end up getting a natural number which satisfies this criteria. So to begin with, we will first select an epsilon. So we'll say that let epsilon greater than 0 be an arbitrary real number. Now, since epsilon is greater than 0, we can talk about 1 upon epsilon. Later on, towards the end of the proof, towards the end of the solution of this problem, we will realize why we have talked about why we are interested in 1 by epsilon. So we can say that 1 by epsilon is also positive, and this can give us the usage of Archimedean property. So therefore, by Archimedean property, we could say that there exists a natural number n naught such that 1 by epsilon is lesser than n. Then, if we take n bigger than or equal to n naught, we get 1 by n is lesser than equal to 1 by n naught, and right from this equation, this inequality, we can say that 1 by n naught is lesser than epsilon. Now let us consider the difference between the sequence, which is 1 by n, and its limit, which is 0. So this is equal to 1 by n, and just we have stated above that 1 by n is lesser than equal to 1 by n naught, and which is in turn lesser than epsilon. This happens for every n greater than equal to n naught. Just removing some intermediate, so we have 1 by n minus 0 is lesser than epsilon for every n greater than equal to n. So therefore we can say that the limit of the sequence 1 by n is equal to 0. Let us take another example. So we want to show that the limit of the sequence 1 upon n square plus 1 is 0. So again, we will first start with an arbitrary epsilon. So let epsilon greater than 0 be arbitrary. Now we will rework to find out the trigger point of the Archimedean property. So before we go ahead, we'll just work on with the difference between the sequence and its limit point. So consider mod of 1 upon n square plus 1 minus 0. This is going to be 1 upon n square plus 1, and we know that 1 upon n square plus 1 is strictly lesser than 1 upon n square. And also we know that 1 upon n square can be lesser than or equal to 1 upon n. The equality will be taking place when n is equal to 1. So if n is equal to 1, we will get n is equal to n square. But if n is greater than 1, then n is always smaller than n square. And if we take the reciprocal, we are going to get this expression on the left. So we want to make this difference, which we have got as 1 by n, to be lesser than epsilon. So you will see a quick rearrangement that you need to apply the Archimedean property to 1 upon epsilon. So since epsilon is positive, we get that 1 upon epsilon is positive, and we could get into action the Archimedean property. So therefore, by the Archimedean property, there exists a natural number n naught such that 1 upon epsilon is lesser than n. And then continuing the steps from above, these steps, we will get mod of 1 upon n square plus 1 minus 0 is lesser than epsilon for all n greater than equal to n. And thus we can conclude that the limit of the sequence 1 upon n square plus 1 is equal to 0. So that's your example 2. Now, as an exercise, I want you to solve this problem and show that the limit of the sequence 3n plus 2 divided by n plus 1 is equal to. That's all for today. In the next class, we'll be continuing with this chapter of sequences, and I hope you learn a lot from this. The PDF of this OneNote will be available on the website. You could look out on Google for MathsWithVips and head to the library section. I will also paste the link in the description so that you can access it quickly. And it's a sincere request that if you have liked the video, please do subscribe my channel and also hit the bell icon to get notified for the upcoming videos. Thank you so much for watching till the end. Have a great day.